In this video, we're going to talk about type checking in COOL. Thus far, we've seen two examples of formal notation used to specify parts of a compiler. Regular expressions were used in lexical analysis and context-free grammars, which we used in parsing. It turns out that there's another formalism which has gained widespread acceptance in type checking, and that's logical rules of inference. Inference rules are logical statements that have the form, if some hypothesis is true, then some conclusion is true. So inference rules are implication statements that some hypothesis implies some conclusion. And in the particular case of type checking, an example or a typical kind of reasoning that we see in type checking is that if a couple of expressions have certain types, then some other expression is guaranteed to have a certain type. And so clearly the type checking statement here is an example of an inference rule. And inference rule notation is just a compact way of encoding these kinds of if-then statements. Now, if you haven't seen this notation before, it will be unfamiliar, but actually it's quite easy to read with practice. And we'll start with a very simple system and gradually add features. So we'll use logical conjunction for the English word and implication for the combination of English words if and then. And now one special thing, the string x:(t) is read that x has type t. So this is a logical assertion saying that x has a particular type. So now consider the following very simple type rule. If E1 has type int and E2 has type int, then E1 plus E2 also has type int. And we can just take the definitions we gave on the previous slide and gradually reduce this to a mathematical statement. So for example, we can replace the if-then with an implication, and we can replace the word and with a conjunction, and now we just have these has-type statements, right? And we had a notation for that, and we wind up with this purely mathematical statement which says exactly the same thing, that if E1 has type int and E2 has type int, that implies that E1 plus E2 has type int. Now notice that that statement that we just wrote out is a special case of an inference rule. It's a bunch of hypotheses conjoined together that implies some conclusion. The traditional notation for inference rules is given here. The hypotheses are written above a horizontal line and the conclusion is written below. And it means exactly the same thing as what we had on the previous slide. Namely that if all the things above the horizontal line are true, these are all the hypotheses, then the thing below the horizontal line can be concluded to be true. And there's one piece of new notation here. This is the turnstiles that are used for the hypotheses and the conclusion. And the turnstile is read, it is provable that. And what this means is that we're just going to say explicitly that something is provable in the system of rules that we are defining. And so the way you would read this is that if it is provable that all of these hypotheses are true, so if it's provable that the first hypothesis is true, all the middle hypotheses, and if it is provable that the last hypothesis is true, then it is provable that the conclusion is true. And COOL type rules are going to have the following kinds of hypotheses and conclusions. We're going to prove within the system that some expression has a particular type. So with those definitions out of the way, we actually have enough to write at least a few simple type rules. So if I is an integer literal, if it's an integer constant appearing in my program, then this rule says it is provable that I has type int. So every integer constant has type int. And here's the rule for add, written out now in the inference rule notation. If it is provable that E1 has type int and is provable that E2 has type int, then it is provable that E1 plus E2 has type int. So notice that these rules give templates for describing how to type integers and expressions. The rule for integer constants just used a generic integer I. It didn't give a separate rule for every possible integer. And the rule for plus used expressions E1 and E2. It didn't tell you what particular expressions they were. It just said, give me any expression E1, any expressions E1 and E2 that have type int. And so we can plug any expressions we want in that satisfy the hypotheses, and then we can produce a complete typing for actual expressions. So as a concrete example, let's show that 1 plus 2 has type int. So we want to type the expression 1 plus 2, And since we know the rule for add, that means we need to construct a proof of the type of the number 1 and a proof of the type of the number 2. And we have a rule for dealing with integer constants, namely we can prove because 1 is an integer constant that it has type int, and we can prove that 2 is type int, and then now we have the two hypotheses we need for the sum expression, and we can prove that 1 plus 2 has type int. So an important property of any reasonable type system is that it be sound. And soundness here is a correctness condition. What we want is that whenever the type system can prove that some expression has a particular type t, then if I actually run that program, if I take E and I execute it on a computer, the value that it returns, the value that comes back after running E, in fact has the type predicted by the type system. So if the type system is able to give types to things that actually reflects what kind of value you get when you run the program, then we say that the type system is sound. Now clearly we only want sound rules, but some sound rules are actually quite a bit better than others. So for example, if I have an integer literal and I want to give it a type, well, I showed you the best possible rule before where we said that I has type int, but it would also be correct, just not very precise, to say that I has type object. Certainly, if I evaluate an integer, I will get back an object because every integer in COOL is also an object, but this isn't all that useful because now I can't do any of the integer operations. And so there are lots of different sound rules. There's not just one unique rule for any given COOL expression that will be sound, but some of them are better than others. And in the case of integer literals, the one we really want is that integer literal has type int because that's the most specific type that we can give to that kind of program. To summarize, type checking proves facts with the form E has type T. And notice that this proof is on the structure of the abstract syntax tree. So for the expression 1 plus 2, we prove something about 1 plus 2, but by first proving something about each of the sub-expressions. So we proved that the sub-expressions had type int, and then we managed to prove that the whole thing had type int. Okay? And so the proof has the same shape as the abstract syntax tree. You can look at this proof as a tree. Now the root of the tree in the case of the proof is at the bottom. Usually we draw the abstract syntax tree with the root at the top. So this tree looks like this, whereas we often draw the abstract syntax tree in the other way around. But the important thing here is that the proof has the shape of the abstract syntax tree, and there's one type rule that's used for each abstract syntax tree node. So there's a very direct correspondence between the structure of the proof and the shape of the abstract syntax tree. And in general, the type rule used for a particular node of the abstract syntax tree, the hypotheses, are going to be the proofs of the types of E's sub-expressions. So whatever expressions make up E, we're going to need types for them first, and the conclusion at that particular node will be the type of the entire expression E. And in this way, you can see that types are computed in a bottom-up pass over the abstract syntax tree. That is, I assign first types to the leaves, like here I know that 1 has type int and 2 has type int, and then the types flow towards the root. I'm able to compute then the next level of the abstract syntax tree and so on. And once I've computed the types of all the sub-expressions of a node, then I can compute the type at that node.